In your role as an IT specialist or systems administrator, you'll likely need to write scripts to automate tasks. A piece of code may start as a simple script that does a single thing, but end up growing into a complex program that handles many different tasks. And no matter the size and complexity of our code, we usually want it to perform well. One important thing to keep in mind, though, is that we should always start by writing clear code that does what it should and only try to make it faster if we realize that it's not fast enough. If it takes you 10 minutes to write a script that will run in 5 seconds and 20 minutes to write a script that will do the same but take 3 seconds, does it make a difference? It all depends on how often you run the script. If you run it once a day, the 2 seconds difference definitely won't justify the additional 10 minutes of work. But if you're going to run the same script for the 500 computers on your network, that small difference means it will take 15 less minutes to run the whole script. So overall, you're gaining time. Of course, it's pretty hard to know in advance how fast your script will be and how long it will take you to make it faster. But as a rule, we aim first to write code that's readable, easy to maintain, and easy to understand, because that lets us write code with less bugs. If there's something that's super slow, then yes, it makes sense to fix it, particularly if the script will be executed frequently enough that making it faster will save you more time than the time you spend optimizing it. But remember, trying to optimize every second out of a script is probably not worth your time. Okay, with that said, let's dive into how we can make our code more efficient. The first step is to keep in mind that we can't really make our computer go faster. If we want our code to finish faster, we need to make our computer do less work. And to do this, we'll have to avoid doing work that isn't really needed. How? There's a bunch of different things to do. The most common ones include storing data that was already calculated to avoid calculating it again, using the right data structures for the problem, and reorganizing the code so that the computer can stay busy while waiting for information from slow sources, like disk or over the network. To know what sources of slowness we need to address, we have to figure out where our code is spending most of its time. There's a bunch of tools that can help us with that, called profilers. A profiler is a tool that measures the resources that our code is using, giving us a better understanding of what's going on. In particular, they help us see how the memory is allocated and how the time is spent. Because of how profilers work, they are specific to each programming language. So, we would use gprof to analyze a C program, but use the C profile module to analyze a Python program. Using tools like these, we can see which functions were called by our program, how many times each function was called, and how much time our program spent on each of them. This way, we could find, for example, that our program is calling a function more times than we originally intended, or that a function that we thought would be fast is actually slow. To fix our code, we'll probably need to restructure it to avoid repeating expensive actions. What do we mean by expensive? In this context, expensive actions are those that take a long time to complete. Expensive operations include parsing a file, reading data over the network, or iterating through a whole list. Okay, and how do we modify our code to avoid expensive operations? Having a good understanding of the data structures available to us can help us avoid unnecessary, expensive operations and create efficient scripts. In particular, we'll want to understand the performance of those structures under different conditions. In the introductory course to Python, you learned about a bunch of different data structures available in Python, like lists, tuples, dictionaries, and sets. Each of them have their uses, their advantages, and disadvantages. Let's do a very quick recap of lists and dictionaries. Lists are sequences of elements. We can add, remove, or modify the elements in them, and we can iterate through the whole list to operate on each of the elements. Different programming languages call them differently. The structure is called array list in Java, vector in C++, array in Ruby, and slice in Go. All these names refer to the same data structure that's fast to add or remove elements at the end. But adding or removing elements in the middle can be slow, because all the elements that follow need to be repositioned. It's fast to access the element in a specific position in the list, but finding an element in an unknown position requires going through the whole list. This can be super slow if the list is long. Dictionaries store key value pairs. We add data by associating a value to a key, and then we retrieve a value by looking up a specific key. They're called hash map in Java, unordered map in C++, hash in Ruby, and map in Go. The map part in those names comes from how we're creating a mapping between a key and a value. The hash part comes from the fact that to make the structure efficient, a hashing function is used internally to decide how the elements will be stored. The main characteristic of this structure is that it's super fast for looking up keys. Once we have our data stored in a dictionary, we can find the value associated to a key in just one operation. If it were stored in a list, we need to iterate through the list. So, as a rule of thumb, if you need to access elements by position, or will always iterate through all the elements, use a list to store them. This could be a list of all computers in the network, of all employees in the company, or of all products currently on sale, for example. On the flip side, if we need to look up the elements using a key, we'll use a dictionary. This could be the data associated to a user, which we'd look up using their username, the IP associated to a computer using the host name, or the data associated to a product using the internal product code. Whenever we need to do a bunch of these lookup operations, creating a dictionary and using it to get the data will take a lot less time than iterating over a list to find what we're looking for. But it doesn't make sense to create a dictionary and fill it with data if we're only going to look up one value in it. In that case, we're wasting time creating the structure, when we could just iterate over the list and get the element we're looking for. Another thing that we might want to think twice about is creating copies of the structures that we have in memory. If these structures are big, it can be pretty expensive to create those copies, so we should double check if the copy is really needed. All right, now that we have a better understanding of when to use each data structure and what actions to avoid, we can look into how to deal with expensive loops. Loops are what make our computers do things repeatedly. They're an extremely useful tool and let us avoid repetitive work, but we need to use them with caution. In particular, we need to think about what actions we're going to do inside the loop, and when possible, avoid doing expensive actions. If you do an expensive operation inside a loop, you multiply the time it takes to do the expensive operation by the amount of times you repeat the loop. Say, for example, that you're writing a script to send an email to all the employees at your company, asking them to verify that their emergency contact information is still valid. To send this out, you'll have a loop that sends one email per employee, and in the body of the email, you'll include the current emergency contact data. The interesting part is how you access the data inside the loop. If the data is stored in a file, your script will need to parse the file to fetch it. If the script reads the whole file for every user, you'll be wasting a lot of time parsing the file over and over unnecessarily. Instead, you could parse the file outside of the loop, put the information into a dictionary, and then use the dictionary to retrieve the data inside the loop. So whenever you have a loop in your code, make sure to check what actions you're doing and see if there are operations you can take out of the loop to do them just once. Instead of making one network call for each element, make one call before the loop. Instead of reading from disk for each element, read the whole thing before the loop. And even if the operations done inside the loop aren't especially expensive, if we're going through a list of 1,000 elements and we only need 5 out of them, we're wasting time on elements we don't need. So, make sure that the list of elements that you're iterating through is only as long as you really need it to be. Let's say you're running an internal website. As part of the information the site shows, it displays a list of the last 5 users that logged in. In the code, the program keeps a list of all the users that have logged in since it last started. And when the program needs to display the 5 latest users, it goes through the whole list and finds out which of those are the 5 most recent. This wastes a lot of time, and if the service has been running for a while, it can take really long to go through the whole list. Instead, you could modify the service to store the user access info in log files that can be read if necessary, and only keep the last 5 logins in memory. So whenever a new user logs in, the oldest entry in the list gets discarded, and a new one gets added. That way, the script doesn't need to go through the whole list every time it needs to display the 5 most recent users. Another thing to remember about loops is to break out of the loop once you've found what you were looking for. In Python, we do this using the keyword break. Breaking out of loops means that as soon as the data we're looking for is found, our script can continue. Of course, if the data is at the end of the list, then we need to go through the loop anyway. But when the data is at the beginning of the list and not at the end, it makes sense to have our code break early to make the script faster. Say you're writing a script that checks if a given username is within the list of authorized entities. And if it is, it grants them access to a particular resource. You can use a for loop to iterate through the list of entities. And when the username is found, you can break out of the loop and continue the rest of the script. One last thing to keep in mind is that the right solution for one problem might not be right for a different problem. Say your service has a total of 20 users. In that case, it's okay to go over this list whenever you want to check something. It's short enough that you don't need to do any special optimization. But if your service has over 1,000 users, you'll want to avoid going through that list unless absolutely necessary. And if the service has hundreds of thousands of users, going through that list isn't even a possibility. Up next, we'll talk about what we can do when the expensive operations are already outside of our loops. In our last video, we talked about how to avoid having expensive operations inside our loops. So, if we have to parse a file, we do it once before we call the loop, instead of doing it for each element of the loop. But what if parsing the file is taking a lot of time, even when it's done outside of the loop? Remember that to make our scripts get to their goal faster, we need to avoid having our computer do unnecessary work. So how can we avoid expensive operations, like parsing a file, downloading data over the network, or going through a long list? If the script gets executed fairly regularly, it's common to create a local cache. In an earlier video, we said that a cache is a way of storing data in a form that's faster to access than its original form. So if we're parsing a large file and only keeping a few key pieces of information from it, we can create a cache to store only that information. Or if we're getting some information over the network, we can keep a local copy of the file to avoid downloading it over and over again. Creating caches can be super useful to save us time and make our programs faster, but they're sometimes tricky to get right. We need to think about how often we're going to update the cache and what happens if the data in the cache is out of date. If we're looking for some long-term stats, we can generate the cache once per day and it won't be a problem. This might be the case for data like how much memory was used on computers across the fleet over the last month, how many employees each department in a company has, or how many units were sold of each product over the last quarter. But if we're trying to look at data where the value as of right now is super important, we either can't use a cache or it has to be very short-lived. This could be the case for monitoring the health of computers to alert when something crosses a threshold, checking the stock levels to see if there's enough of a product to sell, or seeing if a username already exists in the network when trying to create a new one. Sometimes, we can add a check to validate if we need to recalculate the cache or not. For example, if our cache is based on a file, we could store the modification date of that file when we calculated the cache, and then only recalculate the cache if the modification date of the file is newer than the one we had stored. If we don't have a way of checking if our cache is out of date or not, we'll need to add in logic to our program that tries to make a sensible decision. For that, we'll take into account how often we expect the data to change, how critical it is that the latest data is used, and how frequently the program that we're running will be executed. After taking all these factors into account, we might decide that the cache needs to be recreated once per day, once per hour, or even once per minute. Yes, even once per minute might make sense if you have a script that can get executed several times per minute and needs to do an expensive operation that can be cached. That way, only the first execution in a minute will spend time on this operation. The rest will be very fast, but the cache is never more than a minute out of date. And keep in mind that caches don't always need to be elaborate structures storing lots of information with a complex timeout logic. Sometimes they can be as simple as having a variable that stores a temporary result instead of calculating this result every time we need it. For example, say you're generating a report that prints how many users there are in each of the different groups in the network. Now, some of these groups may contain other groups in them, and some groups may even be part of several groups. For example, the Java Release Engineers group would be part of the Release Engineers group and the Java Developers group. How can we avoid counting unique users more than once if they show up in multiple groups? We could have a dictionary with the group as the key and the amount of users as the value. That way, we only need to count the members of a group once, and after that, just use the value in the dictionary. To sum all of this up, remember that you'll want to look for strategies that let you avoid doing expensive operations. First, check if these operations are needed at all. And if they are, see if you can store the intermediate results to avoid repeating the expensive operation more than needed. Up next, we'll look into a practical example of how to deal with some code that's running slower than expected. Remember that meeting reminder script that was having trouble with the dates? The developers have kept working on it. It now sends personalized emails with the name of the person getting the email in the greeting. That's cool, but unfortunately, it seems to have made the application pretty slow. The developers are asking for our help in figuring out how we can make the program faster. So let's get to work. First, we'll need to reproduce the problem and figure out what slow means in this case. One user told us that the problem is visible when the list of recipients is long. To avoid spamming our colleagues while we're testing this issue, we'll send the reminders to a bunch of test users that we've created in our mail server. You might remember that the application has two parts: a shell script that pops up a window where we can enter the data of the reminder, and a Python script that prepares the email and sends it. The part that's slow is the sending of the emails, so we won't interact with the pop-up at all. We'll just pass the parameters we need to the Python script. We'll measure the script's speed using the time command. Let's first call it with just one test user and see how long it takes. When we call time, it runs the command that we passed to it and prints how long it took to execute it. There's 3 different values: real, user, and sys. Real is the amount of actual time that it took to execute the command. This value is sometimes called wall clock time because it's how much time a clock hanging on the wall would measure, no matter what the computer is doing. User is the time spent doing operations in the user space, and sys is the time spent doing system-level operations. The values of user and sys won't necessarily add up to the value of real because the computer might be busy with other processes. Okay, what do we see here? It took our script 0.129 seconds to send the email. That's not a lot, but we only sent the message to one user. Let's try this again with our 9 test users.
2, test 3, test 4, test 5, test 6, test 7, test 8, test 9.
All right, we see that it took 0.296 seconds to send the email this time. That's still not a lot, but it does look like it's taking longer with a longer list of emails. Okay, it's time to try to make this better. How can we find out what's wrong with the code? We could always look at the code and see if we find any expensive operations that we could improve. But in this case, we want to use a profiler to get some data about what's going on. So let's try that. There's a bunch of different profilers available for Python that work for different use cases. Here, we'll use the one called pprofile3. We'll use the -f flag to tell it to use the call grind file format, and the -o flag to tell it to store the output in the profile.out file. Okay, this generated a file that we can open with any tool that supports the call grind format. We're going to use kcachegrind to look at the contents, which is a graphical interface for looking into these files. There's a lot going on with this program, so don't get scared if it takes a while to make sense out of it. As with so many other things, practicing and tinkering on your own will help you get used to what all the different things here mean. Let's look at the information we need now. In the lower right half, we see a call graph, which tells us that the main function is calling the send message function one time. This function is calling the message template function, the get name function, and the send message function 9 times each. The graph also tells us how many microseconds are spent on each of these calls. We can see that most of the time is being spent in the get name function. That's probably the one we should optimize. Let's see what this function is doing using Atom. So we see that the getName function opens a CSV file, then goes through the whole file, checking if the first field in the line matches the email name. And when that's the case, it sets the value of the name variable. There's a couple of things that are wrong with this function. First, once it finds the element in the list, it should immediately break out of the loop. Right now, it's iterating through the whole file, even if the email was found in the first line. But even if we fixed that, it would still open the file and read through it for each email address. This can get really slow if the file has a lot of lines. So how can we make this better? We can read the file once and store the values that we care about in a dictionary, and then use that dictionary for the lookups. Let's do that. We'll change the getName function and turn it into a readNames function that will process the CSV file and store the values we want in the names dictionary. For each line, we'll store the email as the key and the names as the values. And instead of returning one name, we'll return the whole dictionary. All right, we have a readNames function that stores the data we want in a dictionary. We now need to change the way this is called in the send message function. We see that the getName function is being called once per email. To apply our change, we should call the readNames function before the for loop, so that we do it only once. And then, instead of calling getName, we'll just get the value from the dictionary. All right, we've made the change. Let's save our file and profile our script again to see if we manage to make it any faster. The graph looks different now, as we've changed how the code behaves. See how the readNames function is now taking a much smaller portion of time? On the flip side, we see that the message template is the one that's taking the most time now. So, if we wanted to keep making our script faster, that's where we would look next. In this video, we saw how we can use the time command to check how long it takes to execute a program. We then saw how we can combine a profiler and a profile visualizer to figure out where our code is spending most of its time. And finally, We changed our code to avoid doing an expensive loop over and over by storing the information in a dictionary and then accessing the dictionary instead. We've called out a few times already that reading information from disk or transferring it over the network is a slow operation. In typical scripts, while this operation is going on, nothing else happens. The script is blocked, waiting for input or output, while the CPU sits idle. One way we can make this better is to do operations in parallel. That way, while the computer is waiting for this slow I/O, other work can take place. The tricky part is dividing up the tasks so that we get the same result in the end. There's actually a whole field of computer science called concurrency dedicated to how we write programs that do operations in parallel. We won't go into a ton of details here, but we'll give you a brief overview of what you can do. First, we need to understand what the operating system already does for us. Our OS handles the many processes that run on our computer. If our computer has more than one core, the operating system can decide which processes get executed on which core. And no matter the split between cores, all of these processes will be executing in parallel. Each of them has its own memory allocation and does its own I/O calls. The OS will decide what fraction of CPU time each process gets and switch between them as needed. So, a very easy way to run operations in parallel is just to split them across different processes, calling your script many times, each with a different input set, and just let the operating system handle the concurrency. Let's say you want to collect statistics on the current load and memory usage for all the computers in your network. You can do this by writing a script that connects to each computer in a list and gets the stats. Each connection takes a while to complete, so the total runtime of the script would be the sum of the time taken by all those connections. Instead, you could split the list of computers into smaller groups and use the OS to call the script many times, once for each group. That way, the connections to the different computers can be started in parallel, which minimizes the time that the CPU isn't doing anything. This is super easy to do, and for many scripts, it'll be the right choice. Another easy thing to do is to have a good balance of different workloads that you run on a computer. If you have a process that's using a lot of CPU, while a different process is using a lot of network I/O, and another process is using a lot of disk I/O, these can all run in parallel without interfering with each other. When using the OS to split the work into processes, these processes don't share any memory. And sometimes we might need to have some shared data. In that case, we'd use threads. Threads let us run parallel tasks inside a process. This allows threads to share some of the memory with other threads in the same process. Since this isn't handled by the OS, we'll need to modify our code to create and handle the threads. For that, we'll need to look into how the programming language we're using implements threading. In Python, we can use the threading or async I/O modules to do this. These modules let us specify which parts of the code we want to run in separate threads or as separate asynchronous events, and how we want the results of each to be combined in the end. We won't go into the details of how you can do that here, but we'll link to more information on this in the next reading. One thing to watch out for is that, depending on the actual threading implementation for the language you're using, it might happen that all threads get executed in the same CPU processor. In that case, if you want to use more processors, you'll need to split the code into fully separate processes. If your script is mostly just waiting on input or output, also known as I/O bound, it might not matter if it's executed on one processor or 8. But you might be doing this in parallel because you're using all the available CPU time. In other words, your script is CPU bound. In this case, you'll definitely want to split your execution across processors. Now there's a point where adding more parallel processes means things become even slower, not faster. If we're trying to read a bunch of files from disk and do too many operations in parallel, the disk might end up spending more time going from one position to another than actually retrieving the data. Or if we're doing a ton of operations that use a lot of CPU, the OS could spend more time switching between them than actually making progress in the calculations we're trying to do. So when doing operations in parallel, we need to find the right balance of simultaneous actions that let our computers stay busy without starving our system for resources. I recently felt the benefits of applying concurrency. I was working on migrating data that was stored in one format, and I needed to store it in a different format. There were a lot of gigabytes of data that needed migrating, so of course, I wasn't going to do it manually. My first version of the script was taking an average of 1 hour per gigabyte migrated. This was much slower than I expected, so I decided to spend more time tweaking the code to make the migration go faster. I reorganized the logic to have a separate thread per file, which decreased the total time to work through the files, since it now wasn't a linear process. And then, to make it go even faster, I split the work onto different machines, each running a bunch of threads. After all this rearranging to use the resources I had, I brought it down to 3 minutes per gigabyte. Yay! Wow, we may be learning a lot about slowness, but we sure are moving fast. Some of these concepts may feel a little complex, and it's perfectly normal. Take your time. Everyone learns slowness at their own pace. Up next, we'll discuss the different approaches we can take to handle systems as they become more complex. A solution that's good for one problem might not be so good for a different problem. And as a system becomes more complex and grows in usage, a solution that worked well before may no longer be well suited. Let's say you're writing a secret Santa script, where each person gives a secret gift to one other randomly assigned person. The script randomly selects pairs of people and then sends an email to the gift giver telling them who they're buying a present for. If you're doing this for the people working on your floor, you might just store the list of names and emails in a CSV file. The file will be small enough that the time spent parsing it won't be significant. Now, if this script grows into a larger project that handles everyone at your company, and the company keeps hiring more and more people, at some point, parsing the file will start taking a lot of time. This is where you might want to consider using a different technology. For example, you could decide to store your data in a SQLite file. This is a lightweight database system that lets you query the information stored in the file without needing to run a database server. Using SQLite for the data probably works just fine for assigning Secret Santas at your company. But imagine that you've kept adding features to the service. So it now includes a way to create a wish list, a machine learning algorithm that suggests possible gifts, and a tracker that keeps a history of each present given. And since people at your company love the program so much, you've made it an external service available to anybody. Keeping all the data in one file would be too slow, so you'll need to move to a different solution. You'll have to use a fully fledged database server, probably even running on a separate machine than the one running the Secret Santa service. And there's even one more step after that. If the service becomes really, really popular, you might notice that your database isn't fast enough to serve all the queries being requested. In that case, you can add a caching service like memcached, which keeps the most commonly used results in RAM to avoid querying the database unnecessarily. So we've gone from hosting the data in a CSV file to having it in a SQLite file, then moving it to a database server, and finally using a dynamic cacher in front of the database server to make it run even faster. A similar progression can happen on the user-facing side of the same project. Initially, we said the service would simply send emails to the people in the list. That's fine if it's a small group and there's one person in charge of the script. But as the project grows more complex, you'd want to have a website for the service to let people do things like check who their assigned person is and create wish lists. Initially, this could just be running on a web server on the same machine as the data. If the website gets used a lot, you might need to add a caching service like Varnish. This would speed up the load of dynamically created pages. And eventually, this still might not be enough. So you'd need to distribute your service across many different computers and use a load balancer to distribute the requests. You could do this in-house with separate computers hosted at your company. But this means that as the application keeps growing, you'd need to add more and more servers. It might be easier to use virtual machines running in the cloud that can be added or removed as the load sustained by the service changes. These examples show how important it is to find the right solution for each problem. It makes no sense to deploy a multi-server web service with a distributed database for storage when you're only going to have a few dozen users. You just need to pay attention to how the service is growing to know when you need to take the next step to make it work best for the current use case. Up next, we'll talk about some of the issues that you might come across when dealing with complex systems. In large complex systems, we have lots of different computers involved, each one doing a part of the work and interacting with the others through the network. For example, think of an e-commerce site for your company. The web server is the part of the system that directly interacts with external users. Another component is the database server, which is accessed by the code that handles any requests generated from the website. And depending on how the whole system is built, you might have a bunch of other services involved, doing different parts of the work. There could be a billing system that generates invoices once orders are placed, a fulfillment system used by the employees preparing the orders for customers, a reporting system that once a day creates a report of all the sales placed, and possibly more. On top of this, you should probably have backup, monitoring, testing infrastructure, and so on. A system like this can be tricky to debug and understand. What do you do if your complex system is slow? As usual, what you want to do is find the bottleneck that's causing your infrastructure to underperform. Is it the generation of dynamic pages on the web server? Is it the queries to the database? Is it doing the calculations for the fulfillment process? Figuring this out can be tricky, so one key piece is to have a good monitoring infrastructure that lets you know where the system is spending the most time. Say you notice that getting the web pages is pretty slow, but when you check the web server, you see that it's not overloaded. Instead, most of the time is spent waiting on network calls. And when looking at your database server, you find that it's spending a lot of time on disk I/O. This shows that there's a problem with how the data is being accessed in the database. One thing to look at is the indexes present in the database. When a database server needs to find data, it can do it much faster if there's an index on the field that you're querying for. On the flip side, if the database has too many indexes, adding or modifying entries can become really slow because all of the indexes need updating. So we need to look for a good balance of having indexes for the fields that are actually going to be used. If the problem is not solved by indexing, and there are too many queries for the server to reply to all of them on time, you might need to look into either caching the queries or distributing the data to separate database servers. Now, what if when you try to figure out why the service is slow, you see that the CPU on the web serving machine is saturated? The first step is to check if the code of the service can be improved, using the techniques that we explained earlier. If it's a dynamic website, we might try adding caching on top of it. But if the code is fine and the cache doesn't help because the problem is that there's just too many requests coming in for one machine to answer all of them, you'll need to distribute the load across more computers. To make this possible, you might need to reorganize the code so that it's capable of running in a distributed system instead of on a single computer. This might take some work, but once you've done it, you can easily scale your application to as many requests as needed by adding more computers to the system. And finally, make sure that you actually need to do whatever you're doing. Lots of times, as projects evolve, we're left with a scary monster of layer after layer of complex code. If we think about what our system is doing for a few minutes, we might end up discovering that there's a whole piece that wasn't needed at all, and it was making our servers do unnecessary work all along. If all of this is starting to sound too difficult and scary, don't worry. Remember that if you ever need to deal with such complex systems, one of your best tools is to ask your colleagues for help. Up next, we'll try our hand at solving a real-life problem with something complex. Our company has an e-commerce website that includes a bunch of images of the products that are up for sale. There's a rebranding coming up, which means that all of these images will need to be replaced with new ones. This includes both the full-size images and the thumbnails. We have a script that creates the thumbnails based on the full-size images, but there's a lot of files to process, and our script is taking a long time to finish. It looks like it's time to take it up a notch and use something better to do the resizing. We'll start by trying out the current script as is, using a set of 1,000 test images. There's more images to convert, but it'll be easier to test the speed of our script with a smaller batch. We'll execute our program using the time command to see how long it takes. It took about 2 seconds for 1,000 images. This doesn't seem too slow, but there's tens of thousands of images that need converting, and we want to make sure that the process is as fast as possible. Let's try making this go faster by having it process the images in parallel. We'll start by importing the Futures submodule, which is part of the concurrent module. This gives us a very simple way of using Python threads. To be able to run things in parallel, we'll need to create an executor. This is the process that's in charge of distributing the work among the different workers. The Futures module provides a couple of different executors, one for using threads and another for using processes. We'll go with the thread pool executor for now. Now, the function that does most of the work in this loop is processFile. Instead of calling it directly in the loop, we'll submit a new task to the executor with the name of the function and its parameters. Our for loop now creates a bunch of tasks that are all scheduled in the executor. The executor will run them in parallel using threads. An interesting thing that happens when we use threads is that the loop will finish as soon as all tasks are scheduled, but it will still take a while until the task's complete. So we'll add a message saying that we're waiting for all threads to finish, and then call the shutdown function on the executor. This function waits until all the workers in the pool are done and only then shuts down the executor. All right, we've made the change. Let's save our script and test it out. Our script now takes 1.2 seconds. That's a nice improvement over the 2 seconds we saw before. See how the user time is higher than the real time? By using multiple threads, our script is making use of the different processors available in the computer, and this value shows the time used on all processors combined. What do you think will happen if we try to use processes instead of threads? Let's try this out by changing the executor that we're using. By changing the executor to the process pool executor, we tell the Futures module that we want to use processes instead of threads for the parallel operations. Let's save and try this one out now. Wow, this is now taking less than a second to finish, and the user time has gone up even more. This is because by using processes, we're making even more use of the CPU. The difference is caused by the way threads and processes work in Python. Threads use a bunch of safety features to avoid having two threads that try to write to the same variable. And this means that when using threads, they may end up waiting for their turn to write to variables for a few milliseconds, adding up to the small difference between the two approaches. In this video, we looked into how we can add threading support to a Python script to make better use of our processor power. There's still more improvements that we could make to our script, like checking if the thumbnail exists and is up to date before doing the conversion, or adding a second progress bar while waiting for tasks to finish to make it clear that our script is doing its job. We won't go into those here, but if you're interested, you can explore those possibilities on your own.
Congratulations on finishing this lesson in the Google IT Automation with Python certificate. Access the full experience, including job search help, and get the official certificate by clicking the icon or the link in the description. Watch the next lesson in the course by clicking here, and subscribe to our channel for more lessons from upcoming Google Career Certificates.